how derivatives affect the shape of the graph. Let's take a few functions and investigate the intervals of increase, decrease, local extreme values. Let's also look at the concavity and inflection points. Okay, let's start with this example. I was just going through the theorems and properties that I will be applying. Okay, for a given function, we have to find an intervals of increase, decrease, and the stuff that I just mentioned. Okay, let's see. We see function polynomial third degree 1/3 x cubed minus 1/2 x squared minus 2x. That means polynomial functions domain is all of the numbers, all of the real numbers. Okay? This means all real numbers. Or I can even use the set notation x belongs to that interval. Okay, as we know that we need the first derivative, because if the first derivative is positive, function is increasing. If the first derivative is negative, function is decreasing. 1/3 x cubed, the derivative is just x squared, minus 1/2 x squared, derivative is just x, and 2x is just 2, negative of course. And then derivative is 0 if and only if x squared minus x minus 2 is 0. Quadratic expression, we can easily factor out. Product of 2 is 2 and 1, 2, negative 2 and positive 1. Then the zeros are negative 1, this is the value that is giving me 0, or positive 2. Okay? And both of them are in the domain. That means I can name them critical values, critical points, critical numbers. We will try to check the sign of the derivative. That means this is x, that's negative 1, that's 2. And we will test the derivative. Derivative, I think this is the good form. Okay, this is my derivative. And we can take a test value. That means taking a test value like, let's say 3. If I substitute 3 plus 1, 3 minus 2, it's positive times positive, positive. Now I can take different test value. Let's say 0. If I put 0 plus 1, 0 minus 2, positive number times negative number, negative. And then I can do the other, no, I did delete. I can do the other test value. Let's say negative 2. Negative 2, if substituted here, negative 2 plus 1 is negative. Negative 2 and negative 2 is negative. Negative times negative is actually positive. That we can nicely see the sign of the derivative, and I can use the color blue possibly. And we know that if the first derivative is positive, function is increasing. And then if first derivative is negative, function is decreasing. And again increasing. And then we can see this nice behavior increasing, resting, attaining local maximum, and then going down. That means at negative 1, we do have local maximum. And then again, function is decreasing, okay, and resting, which means attending local minimum, the lower one, and then going up. And we almost have the shape of the function. We can see that probably, what color I can use, maybe blue. Probably we will change concavity somewhere here, but I don't know. I have to investigate. But I can say that x at x negative 1, okay, function attains local maximum. At x positive 2, function f attains local minimum. Okay, really good. Now let's test the concavity and inflection points. For the concavity, oh, I don't have enough room. For the concavity, I need a second derivative. Okay, second derivative. The first derivative is x squared minus x minus 2. This one. That's mean derivative is 2x minus 1. 2x minus 1. And for the potential inflection points, I have to find the zeros of the second derivative. Second derivative is 0 if and only if 2x minus 1 is 0. Then x is 1/2. And 1/2 is in the domain of the function. That means probably this is the inflection point, but we have to test that value 1/2. Let's take the second derivative now, which I will be using this. And let's take the test value. I can take 0 and 1. If I substitute 1, 2 times 1 here, minus 1 is positive. If I put 0, 2 times 0 minus 1 is actually negative. That means function is concave down and concave up. And we can nicely see, coming back to this one, this I think looks like 1/2. We will have here inflection point. Inflection point, because inflection point at x 1/2. Function is changing concavity. Concave down, and we can even see on this graph, concave down, and at 1/2 it's changing concave up. And we of course have the local values. Okay, that's the entire graph of the function, and we can see how derivatives affect this. Okay, let's take another one. The same thing, intervals of increase, decrease, local extreme values, concavity, and inflection. X to the power of 4 minus 4x cubed. Again, polynomial, nice and smooth function, all numbers in the domain. X belongs from negative infinity to positive infinity. Let's find a first derivative. Okay, 4x cubed minus 12x squared. First derivative is equals to 0 if and only if 4x cubed minus 12x squared equals to 0. Let's factor out 4x squared, x minus 3, and then the zeros are 0 or positive 3. Both of them are in the domain of the function, in the domain, that's the domain of course. Then they are critical points. Critical numbers. Let's put them on the number line. 0 and 3. Okay, and we will test the sign of the first derivative, and I will be using a product form as always. That's my derivative. And the test value. Let's put 4. If I put 4 here and here, I have positive number times positive number, positive. Let's put 1. If I will put, I am erasing, I will put 1 and 1. I have still 1, because actually x squared is always positive. I don't even have to test it. But 1 minus 3 will give me negative value. Okay, and let's maybe take negative 1. Negative 1, negative 1. Negative 1 squared is positive, as I said. And negative 1 minus 3 is still negative. That means, please note, we do not alternating here and here. That's what we sometimes think, that we will always alternate the sign of the derivative next to the critical points. Not always. Okay, this means that function is decreasing and attaining some critical points, which means probably has a horizontal tangent, but then again decreasing and decreasing, attaining local minimum. We can see we are at the bottom, and then increasing. Okay, that's we do have the intervals of increase and decrease. Actually, I can state an intervals. Okay, that means function is increasing if x belongs to an interval from 3 to infinity. Yes, we can see this increasing. Function is decreasing if x is between negative infinity and 0 and 0 to 3. We may, since 0 is in the domain of the function, we may combine this. Yeah? That means function is decreasing from negative infinity up to 3. Okay, and then at x equals to 0, we can see no extreme values. No extreme values. But at x equals to 3, function attains minimum, local minimum. Okay, really good. What we need else? We need the second derivative. Again, I don't really have enough room, but we can try. Second derivative of the function is, where is the first? That's the first one, right? 4x cubed minus 12x squared. Then the second derivative is 12x squared minus 24x. 12x squared minus 24x. Let me just double check. And then the second derivative is 0. Okay, if and only if. And I can factor out 12x. I will have x minus 2 is 0. And then we can see x is 0 from here, and x is 2. That means at 0 and at 2, we have to still check the sign, but probably we will have an inflection point. Let's test it. I can use, actually I have the graph, if you can see, but okay, you can look at the graph the moment that I am testing the second derivative, 0, 2, and I will be testing the sign of the second derivative. That's this. Let's take a test value, 3. If I put 3, no problem, positive, positive, positive. If I put 1, 1, 1, negative. And if we will put 0, is 0 giving me also 0? Oh, not 0. I have to put a test value which is in the interval, not including 0. If I will put negative 1, I have negative times negative, positive, because I know that is inflection point. Okay, then function is concave up, concave down, and concave up. Okay, that means at 0 we have inflection point, and at 2 we have inflection point. And we can see 0 and 2. And that's what we had above. Function is decreasing, and we know concavity, concave up. And then again, decreasing, but changing concavity. Concave down. And then again, concave up for the entire, but going through the minimum value. We did have this here, right? We knew that something is happening at 0 and at 3. Okay, and then let's solve one trigonometric function. The same thing. Let's investigate the shape of the function. X plus 2 sine of x. We know that domain is all of the numbers, but let's take only the numbers from 0 to 2 pi, since sine of x is the periodic function and everything repeats from after 2 pi. Derivative of x is 1, derivative of sine of x is cosine of x. Okay, derivative is 0 if and only if 1 plus 2 cosine of x equals to 0. Let's solve for cosine, subtracting 1 divided by 2. Cosine for what angle is negative half? Cosine for pi over 3 is half, but we need a solution from the second quadrant and the third quadrant since cosine is negative. That means we will multiply by 2 pi, or 4 pi over 3. That's my critical points. Let's test them. 2 pi over 3 and 4 pi over 3. Both of them are in the domain. That means they are good. They are in the domain. That means they are critical points. Critical numbers. Okay. And we will test the sign of the first derivative. That's my first derivative. Let's take the test values. I know that 0 is not, I can actually do 2 pi, let's say pi, I will start as always from the back side. Okay, 4 pi over 3, I can say 2 pi not 3 pi over 2, that's what I wanted. 3 pi over 2. Cosine if I substitute here 3 pi over 2, cosine at 3 pi over 2 is actually 0. That means 0 times 2 plus 1, it's positive. Then I will do pi. If we will substitute instead of x pi, cosine at pi is negative 1. 2 times negative 1 is negative. 2 plus 1, it's negative. And then I can say pi over 2. Pi over 2, cosine at pi over 2 is 0. Times 2, 0 plus 1, positive number. Okay, really nice sign. Then we know that function is increasing and then decreasing and then again increasing. That means probably we will have like increasing, local maximum, and then local minimum and up. Okay, that means this is local max, local min. Okay, and I can state the intervals. Function is increasing, or I can use my previous symbols. Function is increasing if x belongs from 0 to 2 pi over 3 and from 4 pi over 3 to 2 pi, because we have to stop at 2 pi and start from 0. That's our domain. Function is decreasing if x belongs to the interval between 2 pi over 3 and 4 pi over 3. Really good. At x equals to 2 pi over 3, function attains local maximum value, and at 4 pi over 3, function attains local minimum value. Okay. Now let's look at the second derivative. Maybe we can get the concavity. We need the second derivative. That's the first one, 1 plus 2 cosine of x. Derivative of 1, of course, is 0. 2 cosine of x will be negative 2 sine of x. And the second derivative is 0 if and only if negative 2 sine of x is 0. Dividing by negative 2, I have sine of x is 0. That means for what angle sine of x is 0? For 0, pi, and 2 pi. But we will not look at 0 and 2 pi because that's the endpoints. We will only take the pi. Okay, because 0 and 2 pi is the endpoints of the domain. That means let's check the sign. We can take a test value. I can take pi over 2 and 3 pi over 2, the nicest numbers. If I substitute first, because that's we have to be really careful. This is my second derivative. You can see negative. We can't take sine of x. That will be wrong. This was just the solution. That means substituting 3 pi over 2, function sine is negative 1. Sine of x, sine of 3 pi over 2. Negative 1 times negative 2 is positive. And then substituting just pi over 2, Sine is 1. 1 times negative 2 is negative. Okay? Function is then concave down on that interval. Okay? And concave up. And we do have inflection point because derivative is second derivative is changing the sign. We have inflection point at pi. I can state, it's okay, I can leave it. We know we have everything on that graph. Function is concave up if x belongs to, and concave up is here. Okay, from pi to 2 pi, because we have to cut the domain. And then function is concave down if x is from 0 to pi. Really good. And of course at pi we do have function have inflection point. Okay, it's really nice function. And let's take another trigonometric function, because we always have like some issue with trigonometric. I know it's always a little bit less confusing than the polynomials. Okay, the same thing. I will set up the domain just from 0 to 2 pi. Okay, let's find the first derivative. Negative 2x plus 2 minus 2 sine of x. Derivative is negative 2 minus 2 cosine of x. And derivative is 0 if and only if negative 2 minus 2 cosine of x is 0. Let's solve for cosine. Adding 2 to both sides and dividing by negative 2, we're getting negative 1. Cosine for what angle is negative 1? Cosine for what angle is negative 1? We can use the unit circle, or we can draw a cosine curve. And we can see that's pi, because that's pi over 2, that's 3 pi over 2. Okay? And at pi, cosine is negative 1. Okay? Based on the graph, we do have. And pi is in the domain, that's the critical point. Critical number. Let's test it. Pi. We will test the first derivative. This is the first derivative. We have to remember, we have to take the original one without any simplification. Okay, that's the derivative. Test value, I can take maybe 3 pi over 2, that's after pi, and then substituting here 3 pi over 2, and we're only looking for the sign, positive or negative, not the exact value. Okay, we know that cosine at 3 pi over 2 is 0, times 2 is 0, negative number will stay. And then let's substitute pi over 2. The green one adjusts the test values. Substituting pi over 2, cosine at pi over 2 is again 0, decreasing on the entire interval, because since pi is, we do have some, yes, function is like decreasing and then again decreasing. We will check, maybe it's the inflection point here, okay, but it's definitely no local extreme values. We can say function is decreasing on the entire interval, because domain is from 0 to 2 pi. That means function is decreasing from 0 to 2 pi. Okay. Now let's look at the inflection point. That means we will try to look at the second derivative. Second derivative is looking at that box. We will have derivative of negative 2 cosine of x will be just positive 2 sine of x. And this derivative is 0. I will write here. Derivative is 0 if and only if 2 sine of x is 0, which means sine of x is 0. Sine is 0 at 0, pi and 2 pi, but we will only take pi because 0 and 2 pi are the endpoints. And actually, yes, correct. Look, you see, I was a little bit worried, but pi on my number line, possible inflection points, and let's test the sign of the second derivative. That's my second derivative. And I can pick any values. Again, I will pick 3 pi over 2 and pi over 2 because that's my good numbers. Substituting 3 pi over 2, we know how function sign looks like. Okay, looks like that. 0 pi, 2 pi, pi over 2, 3 pi over 2, x and y. That's mean at 3 pi over 2 is -1. Oh, we don't need the values, of course. It's negative. And positive, it's positive. That means we can see that function is concave up and then it's concave down. But on the graph above looks a little bit better. Can you see concave up and then is actually inflection point and then concave down. Okay, inflection point at pi, at x equals to pi. And we do have concavity, concave up, concave down for the corresponding intervals. Okay, I can say from 0 to pi and then from pi to 2 pi. Really good. That means function is not really increasing, it's simply decreasing. We don't know because we have to investigate more details to get the exact graph, but we fine for now with this. Okay, and then let's do the last exercise today, extremely important. Okay, actually I do have, after this one I have 2 more. Okay, but let's look at this one. This is the graph of the first derivative. Okay, if that's first derivative, I can even say y prime. Actually it's the function y, but we know that is y prime, f prime. Now we have to get some information about a function, about the function which is continuous function. That means it's really good sign for us, really good information. Domain is all of the numbers. Yeah, if we have continuous function, that's we don't have to be worried to exclude the numbers. Okay, on what intervals f is increasing, at what values of x does the function has local maximum, local minimum, and the inflection points, x coordinates of the inflection point. That we can see, and we know, I will do like the test. 0 is the end point, but I will still include 0. Let's mark first zeros of this function, which means zeros of the derivative. 0, 2, 4, 6. Okay, that means that's critical points. Yeah, I will actually, it's also a critical point, it's the end point. 0, 2, 4, and 6. Okay, that means let's test the sign. And now, what is happening between 0 and 2? Function is, the derivative is below, this means it's negative. Between 2 and 4, it's above the x-axis, is positive. Between 4 and 6 is below, it's negative. And then after 6, it's above, it's positive. Perfect, we know everything. Okay, then we know that function is decreasing, increasing, decreasing, increasing. Local max at x equals to 2, local min at x equals to 4, local, am I crazy? Local minimum value. We are at the bottom of the hill. Okay, and then we are on the top, local maximum value, and then local minimum value at 6. Okay, that's we can see we have really nice characteristic, like information from the derivative about the function. And they asking for the intervals of increase. That means I can answer function is increasing if x belongs from 2 to 4 and from 6 to positive infinity. Okay, that means that's A. They want local max and local minimum value. Let's do not make mistake. At x equals to 2, we are at the bottom, we can see function has local minimum value. At x 4, function has local maximum value, and at 6, again the bottom of the whole, I can say this way, function has local minimum value. Excellent. And okay, we have to do another test at the inflection points. That means what I will do, I will definitely remove the green part, and can I remove it? Let's test the second derivative. I know that is probably challenge, but we will try to do it. But we need because I have to, okay, I will remove everything. You can pause the video at the writing for this. Okay, that's me. Now what we will do, now I will draw x and I will try to look at the values that the second derivative is 0. Okay, now looking at the first derivative, we can treat this as a function. Okay? That means if this function is decreasing, for example, yes, we can see decreasing and decreasing, then its derivative, it's negative, right? Which this will be a second derivative. That means I can say, but what is important? I have to find the zeros. That means this will be the zeros of the second derivative. Okay, 1, because something is changing. 3, 5, and this is the moment that we're changing the shape. 7 and also 8. Okay, and now as I said, now as I said, from 0 to 1 function is decreasing its derivative, which is the second derivative. I will put lower, it's negative. And then from 1 to 3 it's increasing, it's positive. And then again from 5 to 7 it's positive, from 8 to 9 is positive. We can actually end at 9, which I did. Now let's use, because I did use the infinity, let's use the infinity. I will not stop this at 9. Okay, and let's put the negatives. That means again this is decreasing, negative, decreasing, negative. Okay, and we can see nice characteristic of the function. Function is concave down, concave up, concave down, concave up, concave down, and concave up. Really nice. And at each this point we will have inflection point. That means inflection points, I mean just the x coordinates. Inflection points are at x equals to 1, 3, 5, 7, and 8. Okay, that's what we do. I did answer this question. Okay, we can see all of the like the horizontal tangent for the first derivative. Okay, and as I said, I have this question. Let's see, and I think I have one more. Okay, but they are nice and easy, multiple choice exam type. Let's see, how many points of inflection does the graph of the function f have if the second derivative is provided? So easy. X squared times x plus 1 cube times x plus 2 to the power of negative 4. I can rewrite this x squared, x plus 1 cube, x plus 2 to the power of 4, but I don't have to. But what we can see, the important numbers, possible inflection points possible, are the zeros. That means 0, negative 1, and negative 2. We all know where this comes from. If I put 0 here, I have 0. If I put negative 1, I have 0. If I put negative 2, I have 0. I will remove my blue thing because I like my formula. Okay, but they are not, that's what you can see. We have to be really careful. I don't think this is the correct answer, because what we have to do, always test the second derivative sign. Negative 2, negative 1, 0. And let's try. Just the test value. If we put 1, if I put 1, 1 and 1, I have, now what we can do, we have x squared and x plus 2 to the power of 4. Even exponents. Doesn't really matter what I put, I will always have positive. That means the main thing is to just focus on x plus 1 to the power of 3. But 1 plus 1, positive cube, positive. No? Oh, I can't write it. Probably my pen is not charged. Okay, that means I was gonna put above that 1, I was gonna put 1. Positive. Okay? Positive. Okay, actually I can do it. Okay, now we do have tiny interval, negative half. If I put negative half plus 1 here, negative half plus 1, it's still positive. Cube, positive. And if I will put negative 3 halves plus 1 is actually negative. Cube, it's negative. And if I will put negative 3, I will have negative number. It's also cube, it's also negative. Okay, that means we can see the second derivative is changing the sign only at negative 1. Function is concave down, and then is concave up. Here is changing the sign. That means this is inflection point at x, negative 1, which means we have only one inflection point. Another way to look at this a little bit faster, because I did the entire, I did analyze completely with the test value. Another way is to look at these exponents. Can you see 2 and 4? I can write here 2 and 4, the even one. That means 0 came from the even and negative 2 came from the even multiple. Negative 1 came from the odd, we can see 3 from the odd exponent. That means when we have even exponents, this means that this function, corresponding function, will never change the sign. That means 0 will be not an inflection. At 0, we will have not inflection point at negative 2. And we can see what's happened. At negative 2, negative, negative. At 0, positive, positive. Could be either way, but the same sign. Negative, then negative. Positive, positive. That means they are not inflection points. Only negative 1. Okay? And then I have similar question here. Having a first derivative, we have to determine the intervals of decrease. So we can see, so nice, because we see the zeros right away. X equals to 1, x equals to 0, x equals to negative 3. Right? That means we do have negative 3, 0, and 1. And the first derivative And testing the values, we know what to do. That means I will do a little bit faster. If I substitute 2, I have positive, positive, positive. And then when I substitute 1/2, okay, you can try to substitute instead of x. You have to substitute, that's what I'm substituting. You have to substitute 1/2. I will get negative number. Then I can substitute possibly 1. I will get also negative number. And if I will substitute -4, I will have, if I substitute -4, I will have positive number, okay? And you probably see what I use. I use the powers. That means what this is telling me. Let's actually finish this. Function is increasing, decreasing, decreasing, and then increasing. And since function is continuous function, x could be any number. Domain is all of the numbers. And function is decreasing if x belongs from -3 to 0 and from 0 to 1. Or correct answer could be from -3 to 1, since 0 is in the domain. Okay, because if 0 is not in the domain, then we can't combine. But this is good. Okay, that we can see that's the final answer. One more thing, and that's not a question, but we can see function is increasing and then decreasing. We do have local maximum. Function is increasing and then again increasing. That means no local extreme values, at 0. And you can tell right away because 0 came from x squared, and this is the even exponent. That means 1 and -3 will be fine, because then we have local minimum and up. That means no extreme values. At 0, of course. But we can see this is the indicator. This tells me, that's the reason that I make the sign a little bit faster. Okay, thank you very much. I hope you will enjoy these problems. Try to solve them again, and you will be perfectly fine in this week assignments. And I apologize for my voice because I'm a little bit sick, and for some, at the end we do have some pen problem. The pen didn't work.